All right. So on the first day of class, I made this announcement about an EV showcase on picnic day. Unfortunately, that's been canceled for some reason, but they are having a different event the day after in Southside Park in Sac. I don't really expect people to go to that, so it's a little harder to get to, but I'm gonna, no promises, try my best to possibly try and organize something else. So stay tuned for that. Just know that we won't be having the EV showcase event during picnic day. Okay. So today we're going to be talking about vehicle efficiency. And sort of as I promised on the poll, first things first, talking about efficiency versus efficacy. So from like a strict physics, engineering approach, efficiency is always a dimensionless or unitless number, right? It's something that's between 0 and 1. So efficiency is usually thinking about, for energy efficiency, the work or energy that you get out versus the energy that you get in. You can never have, right, laws of thermodynamics, you can never have more energy coming out than you put into it. And so this number will always be less than 1. But then when we talk about like, hey, what about like miles per gallon, right? That number is usually 20, 30, 40, 50 miles per gallon. So that's technically referred to as efficacy. But in this class and in a lot of sort of disciplines, we use this word a little bit more flexibly. So I'm going to be saying efficiency, which is really referring to efficacy. And so this is the ratio. It's still ratio of output and input, but because they don't have the same units, it won't always be less than 1. Okay, so your service output. So in the case of transportation, that might be something like miles versus the energy input, which is gallons. So those don't really align. But in this case, just know when I say efficiency, for the purposes of this class, we'll be talking about efficacy. All right, any questions about that? Okay, so the first thing we will talk about is fuel efficiency for gasoline. So hopefully this is a concept that most people are familiar with. I mean, we've been kind of skirting around this topic the first couple of weeks, right? So this is something we usually think of in miles per gallon. So this describes the distance a car can drive given some amount of fuel. And it's a nice metric for vehicles because it allows us to kind of directly compare efficiency between vehicles, regardless of its size, and in a lot of cases, even its drivetrain. So in the United States, fuel efficiency is usually measured in MPG. So this is, right, the number of miles I can travel on 1 gallon of gasoline. This is actually not how most of the other world does it. They measure fuel efficiency in the inverse. So liters per 100 kilometer is the sort of most common form of efficiency measurements around the world. Okay, so I want to talk about some nuance about this. Okay, so let me do a quick example. Some of my grad students have heard of this example already, but you guys can just not answer. Okay, so we've got 2 cars. You have a 20 mpg car, and you have a 40 mpg car. Okay, so maybe I'm like the government, and I want to say, I'm going to put in some resources to upgrade these cars or switch someone to a new car. So for car 1, I'm going to go from a 20 mpg car to a 25 mpg car. So that's plus 5 mpg. Whereas for car 2, we'll do 40 mpg car to a 50 mpg car. So that's plus 10 miles per gallon. So this one gets double the mpg benefit that this one does. So if you were the government agency and you were deciding where to put your resources, would you switch car 1 or would you switch car 2 to save more gasoline? So raise your hand for car 1. No, we got a couple people. Okay, raise your hand for car 2. Okay, it's like split 50-50. Okay, so does anyone actually know why it's car 2? It's a little counterintuitive, right? So let's say I drove 100 miles, car 1, 100 miles. So if I were driving in a 20 mpg car, how many gallons of gas would it take me to drive 100 miles? Yeah, 5 gallons. So 5 gallons, okay. And if I drive 25 mile per gallon car and I go 100 miles, how many gallons? 100 divided by 25, right? So 4. So 4 gallons. Okay, so switching this car would save me 1 gallon for 100 miles. For car 2, 100 miles, hopefully you can see where this is going. 100 divided by 40 is 2.5. 2.5 gallons. 100 divided by 50 is 2 gallons. So this would be a total of 0.5 gallons. So if you, even though this gains double the mpg, it saves only half the gallons of gasoline. Okay, very counterintuitive. So this is known as the mpg illusion, and this is actually why for consumption purposes, if you want to measure how much gasoline you're consuming, it's actually better or less counterintuitive to use this measure where you have the gallons on top and the miles in the denominator. And that's because mpg is like a 1/x, right? And so analogously, the way you can think about this is like switching people from like a really fuel efficient car. Let's say if you want to switch people from like a Honda Civic to a Toyota Prius, the improvement in efficiency might get you less than if you were to take someone from like a Hummer to like a slightly less dirty truck. Because at the bottom, you're getting disproportionately larger fuel and emission savings. Okay, I know it's a little counterintuitive. Hopefully everyone can see how the sort of numbers work out here. Yeah, it's actually a fairly straightforward concept, but it's so sort of counterintuitive that this actually one sort of page paper was published in Science, which is a very sort of prestigious journal. But this is like pretty simple algebra. It's actually very interesting. There's been a lot of work in this area where people go and ask like car buyers or even fairly knowledgeable folks in the transportation field about like fuel consumption, and very, very few people are able to kind of do the math correctly. You kind of try and do it intuitively, but it's hard to do it correctly. Okay, any questions about this concept? This is also going to play out into the way we think about efficiency for electric vehicles, right? We can have the kilowatt hours, which is equivalent to your gallons of gasoline. You can have that kilowatt hours per mile, or you can have miles per kilowatt hour. It's already kind of shaking out to look kind of like MPG, unfortunately. I think that's maybe worse in some ways because of this effect. But the other way with kilowatt hours in the numerator is also actually somewhat common. So maybe there's still time or hope that will that unit will prevail. Okay. So when you go to buy a car, oftentimes they have these kind of pasted in the window, or you get these little flyers from the car dealership that will tell you a little bit about efficiency and some of these things here. So we're going to talk about like fuel costs and how to calculate this in another class. But today we're going to try and understand kind of what these things mean. So this particular sheet is for a plug-in hybrid vehicle. So it actually has both the electricity efficiency as well as the gasoline efficiency. If you were just looking at a gas car, you would only have this guy over here. And if you were just looking at an electric car, you would have this person or this number over here. For the gas car, okay, you're given this number. And so hopefully everyone, again, knows what this means. There's this thing that says combined city and highway, and we're going to talk about that today. Over here, oh, actually, I should also mention that they are starting to do it, the consumption as well, right? You can see right here, 2.6 gallons per 100 miles, which is just the inverse of this. And so it's there, but it's featured kind of less prominently. But this is actually going to help you way better understand the fuel consumption of the vehicle than trying to calculate it from this. Okay, for here, we've usually been talking about this kind of number, right? Either the kilowatt hours per 100 miles or miles per kilowatt hour, either way. But there's also this metric called miles per gallon E, which stands for equivalence. And so we'll talk about what that means right now. I personally think it's kind of a silly metric, but it's a way that they're trying to get people to at least use something that they're somewhat familiar with. So if you use MPG, then maybe you get like a relative sense of the efficiency in this metric that you're kind of used to. It doesn't really make a lot of physical sense. So this is right as a way to compare gas cars to electric cars, which is fair, right? Because if you say, oh, I want to look at a 50 MPG car versus a car that's like 35 kilowatt hours per 100 miles, like how do I compare that? So this, I will say this does let you do kind of a direct comparison. But the way it's calculated is that you basically convert the electricity used, right? So your kilowatt hours into gasoline based on the energy content of the fuel. So 1 gallon of gasoline is equal to 33.7 kilowatt hours of electricity. This is actually a pretty interesting number, right? So we said that a Tesla has a 70 kilowatt hour battery, which means that the energy content of it would be equivalent to having a 2-gallon gas tank. But the part that gets confusing is that, yeah, that's the energy content, but a Tesla could, if you're thinking about it in that way, could use those 2 gallons of gasoline way more efficiently than an electric car can. Okay, and so we will look at that. Okay, so from the perspective of MPGE, let's look at some examples. So this is a little timeline thing that I'd shown before. And this time I've included all of the efficiencies or the relative efficiencies here, based on the size of the battery and the range that it has. So if you just divided out this number, you could figure out what the efficiency was in the common terms that you would want. So like kilowatt hours per 100 miles, miles per kilowatt hour, or even MPGE if you use that metric of conversion. So that would be something like 40 divided by 151 divided by 33.7. Okay, or sorry, multiply by 33.7. Okay, any questions about doing those sorts of calculations? This will be featured on future homeworks. Okay. So getting back to this idea that if you do the mile per gallon direct conversion, that it's not kind of the most sensible thing to do. Okay, so if we look at a gas car, so you've got your fuel source and then your combustion engine. So what does this look like? You have gasoline coming into here, okay, and then you have out of the combustion engine, you have useful work, right? This is this green part. So this is something like 20 to 35% of energy in the gasoline is translated into sort of mechanical energy, right, which goes to rotate the wheels. And then you've got this big red arrow here, which is indicating that of the energy content coming in from gasoline, you're actually losing most of it. Okay, so 65 to 80% of energy in the gasoline is lost to heat in combustion and some friction as it kind of goes through your drivetrain. If you could do it sort of like perfectly efficiently, right, you wouldn't get any heat losses. So there's a lot of energy in the heat coming out of the engine. So if we think about it in terms of sort of the fuel content per mile, this is something like 0.03 to 0.04 gallons per mile. Okay, so what about for an electric car? Pretty similar, right? Except that here you've got your battery, and instead of the engine, this is your electric motor. So you have electricity coming in instead of gasoline, and you'll notice the green arrow here, proportional to the red arrow, is much bigger. And for electricity, the losses are much smaller. So 60 to 75% of the energy in the battery is translated to move the vehicle. Actually, a large portion of this is actually considered heat loss from stopping the vehicle. But if you are using regen, which most of the time you will be for electric vehicles, this number is actually closer to like 80 to like high 90%. And most of these losses, as I was saying, is lost to friction. Okay, and so in this sort of comparison between these guys, right, you can see that the relative losses here are much smaller than the losses in the combustion of fuel. And so the statement that electric vehicles are more efficient than gasoline vehicles is true. However, oh yeah, and I should say, right, so this number, if I wanted to kind of compare these directly, is about one-ish kilowatt hours per mile. And so when you think about an EV compared to that number, right, in this example, it's like 3 times more efficient. You're usually on the order of 3 to 5 times more efficient, just looking at this kind of scope here. I will mention that this is not necessarily the best comparison. And that's because there's some other stuff that happens here, right? So this electricity is not what we call kind of this primary energy source. And so this had to be generated from something. Okay, and so depending on what is producing the electricity, if you think about the sort of raw fuel source, the efficiency, the comparative efficiency numbers would look a little bit different. And so here, this is an example of a natural gas plant. And that plant has some efficiency for fuel that comes in versus electricity that goes out of it. And so natural gas combined cycle plants, in this particular example, might be something like 50 to 60% efficient. Okay, and so one way you might think about this is like, this is almost kind of like the engine of the car. And so a natural gas plant is still a lot more efficient than your car engine. And so at the end of the day, like even taking into account the sort of upstream losses, the electric vehicle will still be more efficient, just not necessarily to the same extent. So when we talk about EV efficiency, just keep in mind kind of what scope you're comparing to and kind of the bigger overall picture. Okay, so as I was saying, MPGE doesn't really make physical sense because you don't really combust the electricity. So miles per kilowatt hour, same as MPG. So think about the MPG illusion. Thinking about the question in the poll about EV efficiencies, what's the sort of range? These are all of the electric vehicles that are currently available on the market right now, or have been available over the last decade or so. And so you can see kind of the range in efficiency. We were saying, right, the 0.1 to 1. So you can actually see here, the sort of most efficient is on that side, going to the least efficient up here, which is actually at about 1 kilowatt hour per mile, which is a pretty bad efficiency, to be honest. So in the green are plug-in hybrids, and in the red are full battery electric vehicles. And generally, you can see in this picture, right, that the full battery electric vehicles tend to be sort of a little bit more efficient. Yeah. Oh, okay, hang on. Everything in this picture is more efficient than a gas car. Yeah, so these guys are going to be close to, I guess, some of the gas cars. But okay, 1 kilowatt. So these numbers are pretty unusual. Why is it that high? Yeah, I mean, these will be close to maybe some of the average gas cars based on these numbers. But we're actually going to talk about where these numbers come from in a second. And actually, the way, let's see, the way that it compares to reality might be still a little bit better than most gas cars. Yeah. Generally, yeah, kind of excluding these two, like all of these guys are going to be quite a bit more efficient than gas cars. Okay, any other questions? You'll also usually notice a trend where a lot of the more efficient vehicles tend to be smaller. It's not always going to be the case because depending on the technology, like the motor efficiency, for example, in Teslas are well known to be quite good, and so those will kind of pull away from some of the sort of averages, but size usually plays a pretty important role here. And I think these tend to be a little bit less efficient because the drivetrain systems for the electric drivetrains for plug-in hybrids are not going to be sort of quite as good as the sort of full battery electric drivetrains. Yeah.
So this means that like basically every car on the lower end of it is like what is worth. Be that like it's a plug-in hybrid with the gas component.
So you're talking about the green on the left-hand side? Is that what you're saying? Oh, on the right-hand side. Yeah, so that might play a role in some of this. Although I think a lot of these look like fairly larger cars, right? Jeep Wrangler, Cayenne, that's a big SUV. X5, X3, these are both larger vehicle formats. And again, we'll talk about how these numbers are derived in just a second, which will play some role in what these numbers look like. Okay, I made these little charts here. It's kind of interesting just to get a sense of how the size relates. So the darker typically means larger vehicles. So over time, how has efficiency sort of trended? And so right along this axis, these are levels of efficiency. So the steeper the curve, kind of the more efficient, and then the lower the curve, the less efficient. And you can see kind of over time, they're all sort of populating within this region, but typically you would expect sort of darker dots to be sort of closer down and lighter dots to be farther up. But that's getting thrown off a little bit, especially because of Teslas. Okay. So we've been talking about different vehicles having certain efficiency numbers. When you go to the dealership and you want to buy a car and they give you these, pamphlets that tell you how efficient the vehicles are, these MPGs, like how do these automakers come up with these efficiency numbers, right? So the way this works is that vehicles basically get put on these giant like treadmills, essentially. These are called dynamometers. And so these are tools that you can use to measure a bunch of things on the vehicle, like the torque, the RPM, and the Department of Transportation and the Environmental Protection Agency will use these types of tools to determine both the efficiency as well as the emissions rates. And they subject them to what are known as these sort of standardized testing cycles. Okay, so let me take a quick second to talk about this, because now I'm suddenly talking about emissions, right? So there's a direct relationship between the emissions of a vehicle and its efficiency. And that ratio actually stays the same across all different ranges of vehicles, right? So here, for some amount of fuel that I put in, I will have some amount of movement, right? So that's determined by the MPG. And I will also have some set amount of emissions, right? This is a combustion process. So for every gallon of gasoline you put into the car, there's a certain number of hydrocarbons that get combusted. So these two numbers, MPG and grams of CO2 per mile, are directly related, always. So even as MPG changes, the relationship between MPG and emissions per mile stays constant. And the number that the EPA uses to measure this is 8,887 grams of CO2. Oh, this is wrong, sorry. 8,887 grams of CO2 per gallon, not per mile. So I will fix that. Okay. So you may have seen that oftentimes you get a couple different numbers associated with efficiency. You can have like a city MPG, a highway MPG, or a combined MPG. And the reason for this is that, as we talked before, the efficiency of your drivetrain will vary depending on the speed of the vehicle. And so if you're going in a city versus if you're going in a highway, your engine will operate slightly differently, or motor will operate slightly differently. And then also in cities, sort of practically speaking, you have a lot more stop and go, which also affects efficiency a lot, especially if you don't have like a regenerative braking system. And so for engines, typically the sort of optimal speed for the like best operation of your engine tends to be around like 50 to 60 miles per hour. Whereas for electric vehicles, the optimal speed actually is quite a bit lower. The motors tend to operate a lot better, somewhere in the range of like 20 to 30 miles per hour. Okay, so drive cycles. If we look at this chart here, this is speed versus time. So if you are taking your car and you put it on a treadmill, right, and you want to do some kind of efficiency measurement, what you don't want to do is take one car and throttle it, and then take a different car and then just be really sort of moderate with your driving, right? You wanna have a really standard set of what we call a drive cycle, so that you can compare vehicles fairly. And so there are a set of standardized drive cycles that regulatory agencies use to measure efficiency. So the way this works is like, okay, I drive at these speeds, slow down, drive at these speeds, slow down, and you do go through this entire cycle. And this beginning half, right, these are at lower speeds, right? These are like maximum speed of 50 kilometers per hour. So this would kind of replicate what you would see in like city driving conditions, right? You also have a lot of stop and go. So speed up, slow down, speed up, slow down, speed up, slow down. And then in the latter half, you have more kind of highway driving conditions or other sort of urban conditions where maybe you speed up and you have sort of longer periods of time where you are maintaining sort of higher speeds. So they're trying to get some representation of like the different types of driving that you can see in a vehicle by doing these drive cycles. So this particular one is an older drive cycle that's not really being used anymore, called NEDC, the New European Driving Cycle, used in Europe, obviously. Yeah, so it says here, so meant to represent typical car usage. I can tell you that getting this kind of efficiency in the real world would be basically impossible. So you have these 4 urban driving cycles and then 1 extra urban driving cycle for sort of more aggressive high-speed driving. So this part, I guess, is called the UDC, and this part is called the EUDC. Because this drive cycle isn't super realistic, they came out with a new procedure with a bunch of different sort of test cycles called the WTLP, Worldwide Harmonized Light Vehicles Test Procedure. And that looks something like this. So you have a lot more sort of less sort of constant speed types of events. And again, meant to sort of simulate different driving conditions. And again, still standardized, right? So every vehicle would go under these sort of drive cycles to determine their efficiency. And so in fact, if you were to look up a particular car that's sold in North America, that's also sold in Europe, you're almost certainly going to find a different efficiency number for the one in Europe versus the one in the US, even though they're the same car, because, so I'll get to this, the US uses a different sort of test cycle. So again, worldwide standard, attempt to better match estimates and efficiency and emissions with on-road driving real world conditions. Test procedures, again, are standardized across a bunch of other countries. So a lot of countries actually use WTLP, and it's a lot more dynamic drive cycle. Yeah, and some of these, I think some of these driving cycles differ depending on like the size of the vehicle. They'll use maybe a slightly different drive cycle. What I'll say about these is that these drive cycles do a better job of matching efficiency to real world efficiency, but still not that great. Okay, a lot of these cars, or a lot of the efficiencies coming out of these test procedures are still overstated. So it'd still be pretty hard to get as efficient as what these test cycles will tell you. Okay. So in the US, the Environmental Protection Agency has their own set of test cycles. And so before 2007, they used to use this thing called the 2-cycle test, which is just 1 city cycle and 1 highway. Similar to the NEDC that I was talking about before, very conservative driving and really sort of overstated fuel efficiency figures. And then beginning in 2008, they added 3 additional tests, doing high speed running air conditioning and having colder temperatures. And the combination of those is known as the 5-cycle test. So there's a 2-cycle test and the 5-cycle test. Still conservative, but it's a better representation of efficiencies that you see in the real world. Yeah, so what I'll say is like there's drawbacks about using these, right? I keep saying that they're really conservative, but it is nice because it's standardized. So you still have ability to kind of directly compare vehicles, as opposed to, if if a magazine or something like Car and Driver, if they take vehicles out on test drives and they say, oh, this is the fuel efficiency that we get, they might not be really good comparisons because they might be driving them differently, either the driver or in different locations. So the standardization of this is a nice thing. Okay, this is what the test procedure looks like. These were the two that I was talking about in the 2-cycle test, with the city, which is known as the UDDS, and the highway, which is known as HWFET. These are 2 drive cycles that were originally used on these dynamometers. I'm really bad at saying that word. And then they added some of these other cycles. And you can see sort of parameters about these test cycles here. There are some like tricky things about these, right? Like with the AC one, you have AC on under sort of hot ambient conditions. This is important because there are aspects of like the vehicle being used that don't have to do with the drivetrain. So you typically wouldn't see those show up in a drive cycle test. And those are known as off-cycle things in the vehicle. And so the air conditioning is probably one of the biggest ones for that. Running an AC load is actually pretty energy intensive. So being able to measure that is important and keep that into consideration for the efficiency number. Okay, why don't we take a quick break here for 5 minutes, and we'll come back and talk a little bit more about these test cycles. All right, let's get back to the lecture. So a lot of these actually have to do with particular regulations about efficiency and also about emissions, right? So let's say you're an automaker and you look at these test cycles and you're like, huh, let me actually do something tricky here. Why don't I make the car run cleaner? So maybe I'm going to make it so that it can't accelerate as quickly. And maybe I'll operate the engine a little bit differently if you start driving and it sees this. It's like, oh, okay, I know this pattern. I'm doing the UDDS cycle. Let me modify my car to do that, to do it so that I can make my car seem cleaner than it actually is when you're actually driving it. So this is the Volkswagen Dieselgate scandal. So this happened a couple years ago. Actually, our institute here at Davis was the one that got Volkswagen executives in the same room as a bunch of the Air Resources Board regulators at one of our biannual conferences. So that's kind of like our claim to fame in sort of finding out about this. So basically they found this issue where there were like these really, really big discrepancies between vehicles and the sort of emissions coming out of the test cycles for Europe versus the US. And so you can see kind of what that difference looks like here. So this is for NOx emissions. So basically the vehicle you'd be putting it on this treadmill and then it would be like, oh, I know this test cycle. I'm going to change the way my engine operates. And so they deployed a bunch of the software to millions of vehicles that were being produced to activate emissions controls only during testing, but not when you're driving them on the road. Yeah, it was a really big deal. You know, billions of dollars in criminal fines, billions of dollars in civil penalties. Actually, I think even some jail time for executives. And there were like studies that showed, right, like the, in this, there was a study that showed like the excess number of deaths that would happen due to air pollution because of this whole scandal, right? So pretty big deal here. Yeah, and then unfortunately, it's really hard to kind of deal with this particular issue, other than kind of trusting that automakers won't really do this, because this is one thing that you can just game because they know what the sort of test cycles look like, and they can try and take advantage of that. Yeah. You could, but likely you would for some reason or other, you'd probably want to let the automakers know what the cycles look like. And the other thing is that if you change the test cycle every year, that would mean like MPG in 2022 would mean something different from MPG in 2023. And so from like a consumer perspective, you probably wouldn't want you wouldn't want that, right? It's kind of like, I don't want to say false advertising, but it makes things a little bit harder to compare, especially across years. It's not, there isn't, I would say, like a super easy solution to this, other than make it so that, like, if they get caught doing it, it's big trouble, right? Okay. So all of those tests are specific for gas cars. And since electric vehicles have started to come out, actually even in the sort of early 2000s, people were already starting to think about, oh, how would we do this for electric vehicles? And that has to do with kind of how difficult it would be to kind of track kind of the electricity in the battery versus the sort of fuel in the car. And so this is kind of what is done now. This is called the MultiCycle test. This is an SAE standard, J1634. And so this basically replicates the cycles. So here's the UDDS cycle and the highway cycle I was just talking about. But they do it multiple times. And so you cycle through UDDS and highway and UDDS, and then they actually have this sort of steady speed type of thing. And you do this starting with the vehicle fully charged all the way until it's sort of fully discharged. And so this is the way that electric vehicles are run on these dynamometers in order to determine how much energy to go over sort of these distances. And then the criteria to end the test is that the vehicle can no longer maintain this 55 miles per hour once it's sort of fully discharged. And then you charge it full to see how much energy it took to run this entire cycle. Yeah.
So just out of curiosity, is every car that's actually bought going through these multi-cycle?
No.
Just like their
the model.
cars?
Yeah, the model. So I don't know exactly how it works, but like essentially, like Tesla will send probably a couple of these vehicles over, and then they'll test them all, make sure that they're sort of consistent, and come up with a number for these. Yeah. It's a little bit trickier though. There is some nuance here. So apparently this kind of procedure is pretty tricky and expensive. And you're using the dynamometers and a whole range of like instrumentation to do a lot of these tests. And to do something like this can take a really long time. And so they have some kind of shortcuts here. So we'll talk about that in just a moment. There's this adjustment factor. Okay, so in 2021, we'll look at this example here. Looked at the performance of the Porsche Taycan 4S, which is a fully electric Porsche vehicle, similar class to the Tesla Model S. And so the sort of tested highway range, 220 miles versus 320 miles, versus what the EPA range was of 227 miles, which is pretty close to what the Car and Driver magazine measured, versus the EPA range for the Tesla here is 402 miles versus 320 miles. And so here they were off by 7 miles, but here they were off by 82 miles. So a really big difference. So how the heck is that happening? They're using, right, standard drive cycles. So some of it does have to do with the fact that the Tesla is like straight up more efficient. Like the motor, the inverter is a big one. The battery, all of these things are, from a technological viewpoint, more efficient in the Tesla, leading to kind of the higher sort of ranges, but it's not explaining everything. So they also take advantage of this thing called the EPA Adjustment Factor. So after the multi-cycle test, the EPA automatically adjusts the range of the vehicles down by 30%. So this is what I was talking about, where we know like the 2-cycle and the 5-cycle tests are like still overstating efficiency. And so for EVs, they've proactively kind of adjusted some of these numbers that they're measuring to take that into account. I think that's a pretty good idea, because if you are advertising a car that's like 300 miles of range and you're consistently getting way lower than that, like people are gonna start like not trusting those numbers, right? That'd be pretty bad. But automakers are given the option to run a couple additional drive cycles to generate an alternative adjustment factor. So instead of doing this 30% adjustment, they're allowed to kind of do some other stuff to maybe lower this adjustment factor. And so only Tesla and Audi do this. And that can lead to pretty big range adjustments. The other thing that I've kind of heard about, and I'll admit I don't have kind of perfect knowledge here, but apparently because the test cycles are so expensive to run, oftentimes instead of doing this sort of full thing, maybe they'll only do it for a couple cycles, and then they'll extrapolate what it might look like for the rest of it, which is not necessarily a good practice, because the efficiency of the battery, especially sort of on the lower state of charges, might be different than if it was at a high state of charge, and that might lead to sort of inflation of efficiency. So there's like, so when we think about, Tesla's range being so much better and efficiency being so much better than other vehicles, when you look at like EPA numbers or advertised numbers, it is true to some extent that those efficiencies are due to technological efficiencies, but there's also some kind of gamesmanship happening with the way that the efficiency numbers are actually measured. Okay, any questions about that? Okay, so let's say I drove to school, and let's say my next door neighbor also drove to school, and we had the same car. Would we have used the same amount of gas or electricity out of the battery? Why not? Yeah, we drive differently. Maybe I drive like an absolute maniac and my neighbor drives like a grandma, right? So, we get here, and one of us might have used like twice as much fuel as the other one. Yeah, there's a really cool Mythbusters episode. You can check out the link here, where they talk about this this experiment where they like put a bunch of dimples onto a car to make it like a golf cart. And one of the things they found, right? So your mood affects your fuel efficiency more than almost any other sort of attribute, right? Which is pretty true, right? So people who are heavy-footed on the pedal will have a really different efficiency from someone who drives very conservatively. And so, yeah, this is kind of an interesting challenge for thinking about efficiency in general. We think about this sort of standardized number coming out of these test cycles that you kind of just use for analysis. A lot of modeling just uses those numbers, right? But in reality, there is some kind of differences that are happening because of the way people drive. And not only the way people drive, but where they drive, when they drive, what's the weather like, how hot or cold is it? These are all things that will affect efficiency that you have a lot harder time kind of standardizing. There have been some attempts to look at this, right, where I was just showing one example with the Tesla and the Porsche, where this is the gray bar here is what the EPA says, and then like Edmunds, which is a kind of used car selling website, or it's a cars listing website, not just for used cars. They've done their own kind of tests. I have no idea what the Edmunds like testing cycle is, right? But presumably maybe they're taking them on like real world. And so there's going to be differences in the numbers that anyone who's conducting their own tests sees versus what the EPA says. So again, take those numbers kind of with a grain of salt. Those numbers the EPA numbers, again, tend to be a little bit more conservative in the sense that they often overstate the fuel efficiency compared to the real world. But again, just know that, what does it mean to have like a real world efficiency? People drive differently. It's going to be different in sort of different locations. And so at least we have some kind of standardized efficiency metric to work with. Okay, any questions about this? So I did briefly mention on-cycle versus off-cycle. So these are things having to do with the way that you drive your car. For on-cycle, the way that your drivetrain is being used. But there are a bunch of things that don't have to do with the drivetrain that could actually improve efficiency. And so when we get to some of the discussion about regulatory regulation and efficiency, this will come up, but I'll just kind of point this out now. So things like the lights, the aerodynamics of the car can be really big for something off-cycle. Heating and cooling, this is a diagram of a heat pump, which is kind of a new thing for electric vehicles as a really sort of efficient way of heating and cooling the compartment, as opposed to using something like electric heat. This can save actually a lot of energy. And then even like regenerative braking regenerative braking, and actually this is not regenerative, this is start stop for idling. So turning off the engine when you're coming to a stop. can save fuel as well. And that's considered something that's off cycle. Yeah.
That was actually, speaking of cryogenics, that was the question I had. When you're on a dyno, there's no thing actually. So.
Yeah, that's right. And so you can't measure car aerodynamics on a dynamometer. And so, yeah, well, so no, the car aerodynamics. So the reason why this starts to become relevant is like there's regulation that says, okay, cars have to be some fuel efficiency, and we'll give you extra credits if you do off-cycle things. Okay, and so one of the big ones you can get is car aerodynamics. So they're not able to measure that directly off of these drive cycles, but you get rewarded for doing good aerodynamics via these off-cycle tests. Yeah, and so improving fuel efficiency in gas cars. So what are the things that we can do to improve efficiency? So these are some of the things that I've been talking about. So like reducing vehicle weight, low rolling resistance tires, technologies related to the transmission of the vehicle. So having more gears, letting you operate more efficiently at certain speeds. CVTs, dual clutch transmissions. Okay, you don't have to know what all of these are, but basically the idea here is that like regulatory agencies like to think holistically about the sort of suite of available technologies where we can improve fuel efficiency. And there's lots of reasons why, as a government, you would want to do this, right? Anywhere from decreasing reliance on like imported foreign fuels to doing things like addressing climate change. And so these all kind of play a role in the way that regulatory agencies think about improving fuel efficiency. And even though we think about electric vehicles as these like super clean, super efficient vehicles, it doesn't mean you are limited to only improving efficiency in gas cars. And so even in electric vehicles, there are opportunities in the drivetrain to improve efficiency. So here, the battery inverter motor system as the sort of central drivetrain are all sort of obvious places that you could potentially improve to improve the technology. As I was mentioning, Tesla has been kind of ahead of the game in this area. So their motors are quite a bit more efficient than a lot of other automakers who are actually rapidly catching up. Things like having the inverter be sort of very efficient as well can help kind of streamline the efficiency across the board. Yeah.
Inverter is in DC.
So yeah, exactly. So inverter and converter helping convert phases of electricity. Heat pump efficiency improvements is a big one that I was just mentioning. Extremely efficient temperature control. A 1 kilowatt heat pump can generate the equivalent of 2 to 3 kilowatts of heat. That seems kind of like magic. It's like, right, you can't get more out than you put in, but really it's not creating heat, it's leveraging differences in heat between sort of different environments. It's moving the heat around essentially. And that's as opposed to kind of trying to generate the heat directly from, say, like an electric heater. And so that is one of the things that can really help with certain aspects of off-cycle efficiency for electric vehicles. This is already starting to be implemented in some vehicles. I think the newest Teslas use heat pumps. And I know I think the Hyundai Ioniq 5 also uses heat pumps in certain of their trims. Okay, and if you are, if you're an individual, how can you drive an EV efficiently? So this goes to the kind of driving behavior part of things. You can conserve your momentum, avoid fast acceleration and braking. You can operate the vehicle at its sort of highest efficiency range, 20 to 30 miles per hour. Reduce use of heating and air conditioning, maintaining tire pressure. So these are all sort of personal practices that you could have if you wanted to drive more efficiently. I wouldn't say this is something that we would sort of necessarily rely on to do things like addressing climate change or necessarily improving efficiency. Right? These are kind of personal behavioral things that you could do. Although what I will say is that some automakers are kind of helping to make that sort of behavioral that are helping ease the transition to that sort of behavior in the technology of the vehicle itself. So this is a picture of Nissan Leaf kind of driving cycles. There's a button that you can press in the vehicle itself, and you've probably seen this in a lot of other sort of modern vehicles, even in gas cars, where you can have this like eco button. So what does that do? That makes it so that when you hit the accelerator, it kind of keeps the car from accelerating very quickly. Reduces the levels of acceleration when you press that pedal down, and it can do a couple other things. It can like regulate power to other devices in the vehicle that generally will try and make it a little bit more efficient. And so, you know, that's one way of like, if you don't want to be sort of constantly cognizant of driving a certain way, you can kind of essentially program the car to help you do that. By like decreasing sensitivity of the pedal. Okay, any questions about that? Yeah. Yeah. Actually, funny you should mention that. So our institute has actually looked at this specific question, looking at different driving modes that you can select in a vehicle. I don't know if you know Vaish, she's a grad student who has done this. So we, at our research center, did this big set of studies by going around the state asking for volunteers to put these little loggers into your vehicle. You can put them into the OBD port, which is the onboard diagnostics port. So we've done that to, I think, 800 or so cars around the state. And these things will measure everything. They'll tell you where the car is. They tell us where the car is located every second. And they'll tell us what's going on in the car, essentially, like if you're accelerating, if you're slowing down, if you are plugging in the car, refueling, you know, what buttons you're pressing in the car. We can measure all these things. And so in her study, she was looking specifically, I think, at the Chevy Volt, and they have like an eco mode, a mountain mode, a hybrid mode, which is like a charge sustaining mode. It turns on the engine essentially, and was looking at, I think, energy consumption. I don't remember the details of the study, but yeah, we actually have looked specifically at that. Yeah, maybe I can dig up the papers and I'll put it in the readings for anyone who's interested. Okay, last bit here. We'll end a little bit early today. So there's this pretty interesting group of people who do this thing called hypermiling. So this is like really at the extreme of the efficiency spectrum. So this is like, how far can you go? And so people will take like a Tesla out to like a fully charged Tesla, they'll bring it out to, you know, like a test track, and then they'll drive around in circles for 32 hours of driving. And this person got a 606 miles on a single charge, right? And so a Tesla Model 3 is like a 300-mile range. So they like doubled the range of the vehicle. So you would never see that kind of range, right? If you tried to drive a Tesla yourself, unless you went onto a closed course and drove around in circles for 30 hours. But pretty interesting, right? The efficiency can make a really, really big difference. So 66 kilowatt hours, going 600 miles. That's like a 0.1, it's about 0.1 kilowatt hours per mile, which is like way higher than the efficiency of any vehicle today, commercially. So pretty interesting tidbit at the end here. Sounds like it was kind of a miserable experience. You have to do it without AC, and it definitely, yeah. If you ever driven around for a long time without AC, it'll get really hot. And you don't want to open the windows either, because that actually creates a sort of like vortex. It decreases the efficiency of the car, so you just have to like bake in the car for 30 hours. Yeah. Cool. All right. So yes, for science. And with that, yeah, we'll end for today.
Yeah, you just turn on the autopilot.
Yes, actually, that'd be kind of cool, right? If you could do that.